That's ABC, Accelerated Bridge Construction. Yeah. All right, let's go and get started. I apologize to you all. I mentioned this in field design, but I got back from Orlando, Florida yesterday, and I forgot to bring the weather with me. So I am sorry for that. Yeah, darn. All right, real quick, just a few quick announcements, and then I want to take some time and go through some questions regarding homework 2, because I know there are a few of them. So you probably got emails recently about this sort of like video featurette competition or something like that. There's I don't say competition, whatever you want to call it, sorry, in regards to students developing a small little featurette to be posted on the website. The deadline's not till the 28th, so there's plenty of time to do it, but there is a monetary incentive. They're going to judge them, and then the first place video will get $100. Second place will get 75. Third place is 50. I don't know about you, but I mean, I like money. What's it? Yeah, yeah. So, I mean, increase the competition, you know.
If you're the only one, you get 100, 75, and 50.
I don't know about that. I don't know. You have to send that email to those who make those decisions. Okay. Let's talk about the homework. We got questions on the homework, so let's address those. So who had questions and what? I think it was on problem 3. Is that what it was? Okay. All right. 2.3 or? Okay. All right. Let's see. So, okay. So a couple things, and I'll try and walk you through some things. We'll see if we can work some stuff out together. Okay. So first off, if you look, the problem has a uniformly distributed load, but it also has a 30 kip concentrated load 10 foot from the end, right? Everybody see that? Now, you can handle this one of two ways, okay? One way would be to just draw a shear and moment diagram, or you can use the formulas that are present in this guide. Now, for the distributed load, the moment is WL squared over 8. So you could do 2 kips per foot times 30 foot squared over 8, and I think it comes out to around 225 or something like that. I don't know if anybody's done that, but you got that. And now for the 30 kips, you're going to have to go through the guide if you want to use the guide, and ultimately I believe you're going to have to use figure 8, okay? The concentrated load at any point. So if you want the moment due to that 30 kips, it's 10 foot from the edge, so it's going to be 30 kips times 10 foot times 20 foot divided by 30. So what's that? How much? 200. So if you add that, it should be 425. All right. Did that address the question, or? It's still wrong. Okay. All right. Let's see. So when you do your transform section analysis, the width should be 16. The depth, the effective depth, is the 32, not the 36. Okay. So you should have, x and then 32 minus x. Okay. And then honestly, the math should follow straightforward what we did in the in-class example. The area of the steel should be 6 square inches. The modular ratio is 8, so NAS is 48 square inches. And you're still getting the wrong answer? Huh. Okay, now I may have to go through the solution myself and see if there's something else going on. Because honestly, if all those values are right and you're following what we did in the example, you should get the right answer. So what I'll do is I'll go through this, and if there's an error, it's very possible, that F sub C and F sub S are wrong. They're written by people. So how far off are they? Are they a lot off, or 5,000 off? The book says 1,762 psi and then 28,635 psi. So it's not crazy off. It's just a little off. Let me check because not like 1764, like too off. Okay, all right. Let me check because I'm not sure because really what I thought would trip everybody up is the moment, and it seems like the moment is what you're getting right. So I'm not sure. So let me go through this. I'll go through the solution, and if there's anything that you're missing, like let me know. It is possible that the book got it wrong. They get a bunch of grad students to do the problems, and grad students are human beings and they make mistakes. So, but I'll look into it. Sound good? The homework's not due till Wednesday, so you've got plenty of time. I'm going to try and deal with this by the end of business today. So, now, was it just this one, or were there others? Because just this one. Okay. And then the next two are on nominal capacity, right? Which is what we haven't done yet. Okay, good. All right. So, any other questions? Okay. All right. So today what we're going to talk about are really two things. I'm really excited to get to nominal capacity because this is a topic that we're going to be using quite extensively throughout the semester. But I also will probably get into some discussion on ACI requirements, particularly strain limits, some reinforcement requirements, and get into the strength reduction factor, the phi value. You folks in steel design, we use a similar value today because we would have gross section yielding and then it would have a phi value, et cetera. Yes, sir?
Did you guys run assignment sheets?
You are the man because it slipped my mind. Well, I got sort of carried away with the homework and then handing out that, and I just sort of forgot. Thank you. I might appoint you as the ambassador of remembering, or helping me remember to pass out the sign-in sheets. So. All right. Everybody good? Okay, so let's go to this. All right. Okay, so we've been talking for a little while about the evolution of strength and the evolution of behavior in a concrete beam. As we apply load, what happens to the concrete beam? Now, I'm going to jump back a few slides because I want to show you something. I want to show you, let's see, this. Okay, if you recall, this is the stress strain curve for concrete. We're going to take these. If for those of you in steel design, if you missed your homework, it's right here, and it's also posted on Blackboard. I'm just going to leave it right there. Okay, so going back to this is the typical stress-strain relationship for concrete. And it's a very non-linear response. It's curved, right? Okay, it's not like steel where you have a nice little linear curve, and then it plateaus, and then it jumps up. It's not like that, okay? So because of that, that causes analytical issues as you start looking at ultimate capacity. Because keep in mind, ultimate capacity, we're talking about the stresses in the concrete beam. Let me jump ahead a little bit. We're talking about the stresses in the concrete beam at the very end, when it is done, when it can no longer carry load. So if you look at your bending stress profile, you should have a nonlinear curve, okay? And unfortunately, when we start thinking about nonlinear and we start thinking about determining the total force, that involves the C word, a little bit of calculus. We'd have to integrate this curve, and I know you all are just having a hard time containing your excitement when you think about calculus. Am I right? That was a joke, not a very funny one. There we go, getting some laughs. All right. I'm going to use some calculus to help explain how we go about this, but rest easy, we will not be using calculus to determine the strength of concrete beams. Don't worry. It's a lot of add, subtract, multiply, and divide, so not bad. All right. At the ultimate stage, at the maximum capacity, what happens is the reinforcement has yielded. It's reached its Fy, and we're experiencing a fair degree of nonlinear behavior in the concrete, so we need to be able to assess that. Okay? So if I wanted to summarize concrete behavior in general, this is not, I don't want you to, take this graph to the bank, but this is just sort of a general idea of what's going on. For a general concrete beam, what happens is under very low levels of loads, it behaves normally, and then you hit your cracking moment. So we get a little bit of a jump as the steel takes over, the tensile concrete cracks, and then we can keep on accepting moment, okay? We keep on going, we get to the point where the steel yields, then the beam really starts to go, and then we hit our maximum capacity. Sound good? Okay. Now, that was like really serene. Like, that was peaceful. You said sorry, it's peaceful. Next time you need like some death metal or something. Come on. It's some Slayer in the background or something. All right. Actually, that's more appropriate for steel design, heavy metal. Yes. There we go. All right, now we're back. Okay. So, all right. Let's settle down. All right. So, in order to define our approach as to how we're going to assess concrete beams, I want to look at something that's kind of simple. And I know this is going to seem a little strange, but I want to look at moments and stresses, and I sort of want to look at them from two different approaches, okay? So let's take a look at this beam, okay? Now I got a beam. I'm not saying this is a concrete beam. I'm sort of going back to mechanics of deformable bodies. It's just a beam. It's 12 inches wide. It's 20 inches tall. And I want to determine how much moment is required to hit a bending stress of 8 KSI. This is simple, okay? Now, I propose that there's really sort of two ways we can go about this, okay? Now, the first way is to just use sigma equals my over I, our fundamental bending stress equation. So all I'm doing is I'm just solving for the moment. So the moment is the stress times the moment of inertia divided by y, which this should be familiar by now because that's essentially how we do a cracking moment, right? We take F sub rupture, F sub r, the modulus of rupture, times the gross moment of inertia divided by y. Okay, so the beam's 12 inches wide and it's 20 inches tall. So the moment of inertia is bh cubed over 12. Go through and check that out and you get 8,000 inches to the fourth. We've got our centroidal distance, solve for the moment, and we get 6,400 inch kips, or you can convert that to foot kips, however you want to go about that. Sound good? Okay, that's one way to do this problem. Now, here's another way. Another way is to integrate the stress profile. Okay, now let me sort of explain what I'm doing here, and I want you to really follow along and see if this makes sense. Okay, now we're talking about sigma equals my over I, so that should indicate we have a linear bending stress profile, right? So the bending stress looks something about like this, right? So remember, this is the side of the beam that's seeing compression, this is the side of the beam that's seeing tension. Sound good? All right, now I'm trying to determine in this problem how much moment is required to generate a bending stress of 8 KSI. So since it's rectangular and it's symmetric, I'm going to have 8 KSI on the top and 8 KSI on the bottom. Now the integration and the bending moment, basically what I'm doing is I'm taking the area, quote unquote, the area of this stress profile, multiplying it by the moment arm. That's essentially what I'm doing, okay? So let's work this out. So we're going to do this on the top and then we'll do it on the bottom. So let's work up top. So let's start off with the area. The area is 1/2 of base, which is 8 KSI times the height, right? Now let's keep in mind that bending stress profile, and we're going to test out my 3D art skills right here, so bear with me. So here's the beam. All right, here's the neutral axis, down the middle. And that bending stress profile, if I'm just looking at what's going on up top, it's sort of acting along the entire width, right? It looks something like that. Make sense? So it's going to be, this area, 1/2 of 8 times 10, acting over the width, so 1/2, 8 times 10 times 12, right? So that's the, quote unquote, the area, and then the moment arm. Okay, now how far is it from the center to the centroid of that triangle? Well, it's 2/3 of 10, right? Make sense? Now that takes care of the moment generated up top. For the moment generated on the bottom, well, it's the same thing, right? So why don't I just take the whole thing and multiply it by 2? Make sense? Everybody okay with that? All right. Chug it out, you'll get 6,400 inch kips, okay? So it works, all right? Make sense? This approach is quite valuable when you're trying to determine maximum capacity, because essentially what you're doing is you're trying to figure out, okay, here's my material, it can handle this much stress, so what's the moment that will generate that stress, okay? Make sense? All right. Now, the problem is that with concrete, it's highly nonlinear, okay? It looks like that at its ultimate stage because the stress-strain curve goes like that, all right? So if we did this, we would have to break out our calculus skills and integrate. I mean, we didn't have to really do calculus with the triangle because it's a triangle. A triangle's simple. We know the area of the triangle. We know where the centroid is. We really don't have to do the calculus. But for here, theoretically, we would have to do it. Now, what I'm going to do is I'm going to use some calculus to help explain the approach that we use in reinforced concrete design. So in order to explain that, I want to look at this. I want to consider the following curve. So we're going to look at the graph of y equals the square root of x. Okay, and we're going to look at the region bounded from x equals 0 to x equals 1. So would you agree that that region looks something about like that, right? Now I picked this curve because this curve kind of looks like what's going on here. It's not, exactly accurate, but it's close enough for government work to help explain what's going on, okay? Does that make sense? So what I'm ultimately going to try and compute are two things. I want the area under the curve, so the area bounded from x equals 0 to x equals 1, and I want the moment arm, or the moment from this axis, from the y-axis, because ultimately I want the moment from here, all right? Make sense? Okay. Now, how do I compute the area under the curve? Let's just keep that simple. What would I do? Pop quiz. If it's the FE and I need to know the area under this curve from 0 to 1, what do you do? Integrate from x equals 0 to x equals 1, right? So integrate the square root of x from x equals 0 to x equals 1, right? Everybody who successfully negotiated calculus 1 should be able to do that, right? So you go through, chug it out, and do all your, plug in the top number minus, plug in the bottom number, go through and do all that. And you'll get that this shaded area is 2/3, right? Now the moment is just that area times the distance. So we're talking about the distance, from here out here, so that distance, we're going to take that as x, right? So to do the moment, we just do the same integral, only we tack an x inside that integrand. So go through and do the same thing, and we get a moment of 2/5, okay? So I propose that that curve has an area of 2/3 and a moment about the y-axis of 2/5. Everybody okay with that? Everybody good? Now, I don't like integration. Integration, I don't want to do that if I can avoid it. So I propose that we can formulate a rectangular region that looks like that. And I propose we can come up with the dimensions of that rectangular region that will have the same area and the same moment, okay? Because that's what I'm after. Sum of forces, sum of moments. I want the area and the moment to be identical, okay? So what's the area of that region? Well, it's x prime, y prime, right? What's the moment from here? Well, the area is x prime, y prime. The moment is that area times the moment arm. So 1 minus half that x bar, right? Make sense? Okay, so I propose that if the area is this and the moment is this, I want to determine, well, what is x prime and y prime? What do they have to be so that the area is 2/3 and the moment is 2/5? And if you go through and chug it all out and do your two equations and two unknowns and plug and chug, you will get that the X bar for that box has got to be 4/5 and the Y bar has got to be 5/6. So to summarize, I propose that this region and that region have the same area and generate the same moment. Everybody okay with that? That region on the right is a whole lot easier to deal with than the region that's on the left. Okay? The region on the right, it's just x times y, and the moment arms are really simple. No calculus, right? No integrals. Everybody okay with that? Again, I know you all have had your limit with all that stuff. So. Oh, yeah. We're back. All right. Okay, everybody okay with this? Okay, I want you to understand this philosophy because this is incredibly important to what we're going to be doing throughout this semester. So we do something very similar when we're assessing the maximum capacity of a concrete beam. We employ what's called the Whitney stress block approach. This is an approach that's been around for a while. It's been around since the late 30s. It has not changed since then. It will not change from now. This is, by and large, the simplest but most effective method that we can use to determine the maximum capacity, moment capacity of a reinforced concrete beam. So here's how we go about this. So in reality, at the maximum moment, the stresses in the concrete look like this. Nonlinear, confusing, we really don't like dealing with that. Okay? We are going to simplify this with the following stress block. Okay? So the width of that stress block, the stresses are always taken at a constant 0.85 FC prime. Okay? So remember, you know, we reduced the dimensions of that box a little bit. It was like 0.8 and 0.833 or something like that. So to give you kind of an idea of the numbers, the width of that stress block is 0.85 FC prime. The depth is related to two factors. Number one, it's related to C, which is how deep you are to the neutral axis, and it's related to a term called beta 1. And beta 1 basically just changes depending on the type of concrete you're looking at. For instance, if you're using 4 KSI concrete, beta sub 1 is 0.85. But if you use something like 8 KSI concrete, it drops down to 0.65. Ultimately, it's just a lookup. Okay? But the point I want to keep in mind, this will always be 0.85. This beta sub 1 can change. Okay? Make sense? All right. So what I want to do is I want to look at this beam, and I want to determine the maximum moment capacity of that beam, the M sub n. If I start bending it, at what moment will it fail? Okay? Sound good? Now, right now, I'm just giving you beta sub 1. We will use it and learn how to look it up later, but for now, I'm just giving it to you. All right? B is 10 inches. The effective depth, D, is 23 inches. Okay? For the bars, we're using 3 number 8s. We're not using 3 number 9s. So that will change some things as we go. Everybody good? All right. Give me a moment. No pun intended. I still got it. All right. Okay. Okay, so this is example 5. And we're going to go back to this problem later because we're going to go back and we're going to assess some of the ACI limits with this beam as well. Okay, now we're going to start off to list a few facts that we're going to need. So help me out with a couple things. First off, what is FC prime? 4,000 what? Oh, PSI, and that equals 4 KSI. I'm probably going to operate more in KSI for this just to keep the calcs a little manageable. Now, tell me something about the grade of the rebar. What was the grade for the rebar? Grade for the rebar was 60. So what is F sub Y? Anybody? If it's grade 60, it's just 60 what? There we go. All right. Now, let's see this. All right, and I see Mr. Watson's on the slide. It's slide 63 if you're interested. But we have our reinforcement. Our reinforcement is 3 number 8 bars. So what is the area of steel going to be? It's going to be 3 times what? 0.79. What does that come out to be? Do I have a second on that? There we go. All right. All right, sound good? Okay. Now, I'm going to draw some schematics out, and I think the best way of learning, or starting to memorize some of these symbols and terminology and things like that is to just draw it out. Okay, so let's document some stuff. So I've got, now let's keep in mind what we're doing. Let me go back to sort of my 3D art representation right here, because I'm gonna sort of reference that as we go forward. So I've got, here's my neutral axis that looks something about like that, right? Now for this beam, I've got 3 bars. We'll say, a bar here, a bar here, and a bar here. And keep in mind they continue on throughout the beam, right? They're just going into the cross section. Sound good? Okay. All right. So the beam looks something about like this. All right. Now, what I'm going to do is this. I'm going to say that the neutral axis extends somewhere out like this. So this is the neutral axis. Because I'm going to draw some images sort of in there. Okay. Now, we've got rebar down here. So help me out with some dimensions. So what do we call that dimension right there? D. There we go. All right. What do we call this dimension? There we go. All right. Now, from here to here, what is that? That's C. There we go. So C is the distance from the top of the beam to the point where there's 0 stress or strain, really 0 strain. That's what's going on with C. Now, let's also recognize what's going on with the stresses in reality. So if I look at my bending stress, my concrete looks something about like this in reality. And we'll say that the top of the beam is sort of right there. So we've got this going on. We'll say that, compression is sort of going to the left. So the rebar is supplying the tension. So we've got some tensile force right here. And then all in all of that force in this nonlinear region of the concrete, that's going to be my compressive force here. Now, what fact must always be true about that compression and that tension? They're equal. Compression has to equal tension, otherwise the beam is running away from you, okay? So the compression has to equal tension. All right. Now, this is nonlinear. I don't like dealing with nonlinear, so this is how we're going to simplify this. Okay. Now, let's start off with the steel. So I'm going to have some tensile force generated from the steel right here. So tensile force. Now, you steel design folks can probably guess how we're going to compute the force generated by the steel. But even if you're not in steel design, we're going to assume that the steel yields. So what's the stress? Okay, that's a good point. That would be the E. That would be the Young's modulus. But I'm talking about the stress. Like, what stress does it reach? 60,000 psi or 60 ksi. Now that stress must be over a given area. And ultimately, what's that area going to be? Area of the steel. So, yeah, exactly. So I propose that to compute this tensile force, it's got to be AS FY. Sound good? Okay. Now, that's the tensile force. The compressive force, again, nonlinear region, I don't like that. So what I'm going to do is this. I'm going to have this be idealized something like that. That's a good question. And it goes into that's a good question. It goes into what we did here, okay? This idealization generates the same area and the same moment, but the rectangle doesn't touch here in order to match the equilibrium. Does that make sense? Yeah. So it's really, the easiest way to say it is because this didn't touch the neutral, this didn't touch over here. Make sense? I propose that if it did, it'd be a tough time coming up with a region that had the same area and the same moment. Because you'd only have one variable. You'd only have the height, but you'd have two unknowns. That's a good question. Everybody good? Okay, now. Where's my full screen? There we go. Okay, now the width of this box is 0.85 FC prime. Now, the height of this box is what? Like, how tall is it? Y'all have that on that other slide? What's that? C times beta 1, or just a simple, the first term is A. Does everybody see that? This is A right here. Everybody okay with that? So this is A. This height right here from there to there, that is C. What I really want to be delineated, here I can do that A a little better. What I want to be delineated is the difference between what is A and what is C. Okay, everybody okay with that? A is the depth of the stress block. C is to the neutral axis. Sound good? Now another point, just so we're clear on dimensions, help me out. How far is it from the top of the beam to the steel? 23 inches, or from some symbolic, it's D. Sound good? Are my D's and my A's looking separate enough? You think it'll pass? Good enough for government work. There we go. I like it. Okay. Now, how would I compute the compressive force? Okay. For the tensile force, it was the area times Fy. So you tell me, how would I compute the force in compression? Say it again. There you go, AB. Because let's keep in mind, if I go up here to my little 3D image, what we've got going on is a stress field that is acting sort of like this. Right? You know, it's that stress block. So the depth of that stress block is the 0.85 FC prime, but the area is AB, right? So in section view, what we really got going on is we've got this region in compression. Does that make sense? Okay. Now, help me out. You agree that compression equals tension, right? It's got to equal tension, otherwise the beam's running away from you. Yes, sir.
So B1 equals 0.85. Does that have anything to do with the top dimension of the stress block?
No, it does not.
So that's always the same no matter what.
Yes, exactly right. The top is always the 0.85 FC prime. It is, let me say, it is possible that beta 1 also equals 0.85 FC prime. Coincidence, is what I'm getting at.
So it's a coincidence. It's
Yeah, it's not always.
Okay.
Not always. And we'll talk about what that is later, okay? Like how would you compute beta 1 for different FC primes? All right, we will get to that, okay? Sound good? Now help me out. If you agree that compression equals tension, answer me this. What don't we know? A. We don't know A. We need to determine how deep that stress block needs to be such that C equals T. Sound good? All right. So if C equals T, and that's 0.85 FC prime AB equals AS FY, then what's A? There we go. I'm waking y'all up. There you go. There we go. So let's plug and chug. Tell me what we got. What's AS? There we go. Inches squared, right? What is FY? There we go, 60 what? All right. 0.85 times what's FC prime? 4 what? KSI. And B, what's B? 10 inches. Now, what are the units going to be when this is all said and done? Inches, right? The KSIs are going to cancel, and I got square inches over inches, so it's going to be inches. All right. Do some plugging and chugging. Tell me what you get. 4.82 or 182? His words. Not mine. Reading my mind. Are you an X-Man? Is that what it is? All right. Did everybody get this? Okay. Now, everybody good so far? Okay. All right. Now, help me out with this. Okay. A moment is essentially, in its basis component, a force acting over a given distance, right? Or if I have a force couple, let's go back to statics. All right, has everybody got this? Okay, all right. So, call from statics. If I have some, force going like this and some force going like that, so F, and then there's some moment arm in between them, the moment is just Fz. Force times the distance, right? Okay, so help me out with this. Let's look at our beam, okay? I'm going to go back a slide real quick. In fact, here's what I'm going to do, because I'm lazy. And Control V. I hit Control C. Okay, all right. So help me out. So a moment equals a force times a distance, okay? So if you want, what you could do, remember if you have a distributed load, you can sort of idealize that as you've got, the single concentrated load right there. Remember that from structural analysis? So which force should we use, C or T? It doesn't matter because C equals T, right? Now, I'm lazy, so which one should I use? C, T. I only have to multiply two things together as opposed to four. So our force is going to be, so how about this? So our force is going to be T, which is AS Fy. So there's that. Now, our moment arm. How far is it symbolically from this force to that force? Say again, D minus A over 2. Does everybody see that? Because from here to here it's D, and then we drop down half a depth, right? So D minus A over 2. Does everybody see that? I propose that the equation to compute the nominal moment capacity of a reinforced concrete beam, a singly reinforced, mind you, is AS Fy D minus A over 2. One of the most fundamental equations we use this semester. Period. Make sense? Let's start plugging and chugging. So what do we got? AS is Fy. There we go. Getting y'all trained up, the units and everything. D is, oh, yes you do. 23 inches minus, and what do we got for A? There we go, 4.182 inches over 2. Now, before we do anything like with the calculator, when we plug and chug, what are the units going to be in? Inch kips, right? Because it's all kips and inches, and it's a moment, right? And you can follow it along, because square inches times KSI will give you kips, and then kips times everything in here, which is inches, so inch kip. So what do we get? 198. 0.2 or something like that. 2973.2. Do I have a second on that? All right, all right. You got outvoted, Mr. Davis. I'm sorry. No biggie. All right, so that's inch kips. I'm not a fan of inch kips ultimately for moment. So if I want to convert that to foot kips, what would I do? Did you say something about a 12? Remember, it's inch kips going to foot kips, so we divide. Yeah, it'll be a smaller number, yeah, so you divide by 12. So what do we get? Funny guy, funny guy. What do we got? 247.8 foot kips. Now, if you compare that to the cracking moment, it's going to be, this is going to be a much larger number, but there we go. Not too bad, right? All right, hold on. We got two questions. Let me get to yours in a second. But to answer your question, yes. But make sure that the cross-section you're looking at makes sense. Like if it's a rectangular singly reinforced beam, I got no problem with that at all. But just make sure that you're not just applying a one-size-fits-all approach to all the problems. I say singly reinforced. You might go, what do you mean by singly reinforced? Singly, yes. Singly reinforced beams are beams where we're only considering, everybody want to pay attention to this. So singly reinforced beams are beams with reinforcement only in the tensile region. If we had reinforcement up here, they would be doubly reinforced sections. So that's what a doubly reinforced beam is. No, yeah, if you have both. You can't have reinforcement only in the compression region because then the beam would be in the river. Yeah. Yes, you had a question. Yes, sir. All right, okay. Everybody? Well, it's still all seeing tension. You can have reinforcement in 2 or 3 layers. There's nothing wrong with that at all. Yeah, because there's only reinforcement that's acting in tension. No, it's a good question, but honestly, actually, kind of what he said, because then it's not doing any good. No. Hey. This is important stuff. Let me say this: for your reinforcement to be effective, you really want it seeing tension. No, this is important. You really want it seeing tension. So you want to drop that reinforcement as much as you can. In fact, the only reason it's not further down is because you have to have some degree of cover for things like corrosion and things like that. So it's got to be raised up a little bit so that the concrete can protect it against salts and the environment and things like that. Let's move on. That's a great question. Okay, if you had, no, this is a good question. If your reinforcement was staggered, if it was in a weird pattern, you would literally just look at the reinforcement by itself and ask yourself, what's the centroid of that pattern of reinforcement? And just say D goes from the top to just that centroid. But from a practicality standpoint, by and large, your rebar is going to just be in a number of rows. So it'll be sort of like a grid-like pattern, and you'll just say right in the middle. But that's a great question. So, yes, sir.
What about I was just at the state of they use beam.
That's a great question. So what you're talking about are pre-stressed beams, and pre-stressed is a whole nother can of worms. Honestly, pre-stressed concrete is a class all by itself. Like you all are taking reinforced concrete. Pre-stressed is a class all on its own. Essentially, to answer your question quickly, what I'll say is you will have an A sub S, an area of steel. Then you'll also have an A sub P, an area of pre-stressing cables. And then it's all about just determining the usable stress of your cables, and then it's still C equals T. It's a whole nother can of worms, though, because pre-stress, unlike just regular reinforcement, has a lot more complications in regards to its behavior. See, over time, the force that's in those cables will dissipate because of things like relaxation, the environment, shrinkage and things like that. The concrete will creep. You'll have slip from the jacks at the very end. So all that will cause the forces in that concrete to dissipate, or in those cables to dissipate. Usually, to give you a rough estimate, from day one until its service life, you can lose 20% of that force. So assessing that is a can of worms. Yes, sir.
So,
No, you're fine.
But when you're looking at a pre-stressed application, obviously the reinforcement is put into tension, but then once the tension is released into the beam, is that assumed to be a compressive force in the tensile region?
Yeah, exactly. The easiest way to explain it is this. Okay, imagine that there was a hole drilled in this wall, okay, and there was a rope sticking out of it. Now, let's say I want to pull the rope. How am I going to do that? Put my hand here and pull on the rope. What am I doing to the wall? I'm pushing on it. I'm applying compression to the wall. So the idea is, if I have a beam that has compression on the top and tension on the bottom, but I lock in that pre-stress on the bottom, theoretically, I can eliminate the tension. The tension's gone. You say, well, doesn't C have to equal T? Well, that's if there's no force going like this. If you take that force going like this, you'll still get sum of forces equals 0. The benefit is that you can take a beam that might have needed to have been this big and make it this big. Okay, that's the benefit, because concrete loves to be in compression. Make sense? Okay. Any other questions? This is good stuff. All right. Before we end, let me at least kind of very quickly mention some ACI requirements. A lot of this stuff's pretty basic, but I want to sort of knock some of it out. So, in terms of flexural resistance, we talked a lot about stresses. The concrete will be 0.85 FC prime, and then our stress block varies. One of the things, though, that will change is that, or that we do need to discuss, is the strains, right? Remember, in mechanics of deformable bodies, there's stresses and then there's strains, okay? Strains, we assume very linearly. They're always a linear region. So from the top down, that is C, okay? So that's where C comes into play. We use that to compute the strains, okay? The reason why that's important is because we have limits not only on usable strain for the concrete, but also usable strain and what the strain needs to be in the steel. Now, when we start looking at strains, one of the first assumptions that we make is that no matter what type of concrete we're looking at, the maximum usable strain in the concrete is 0.003. That will be what we always use, regardless of if it's 4 KSI or 6 KSI. We basically say that right around here, that's about a maximum usable strain that we can use for concrete, regardless of its grade. We will use that relationship that this is 0.003, and looking at this height, we can just use similar triangles to see what is this strain, okay? And understanding what this strain is important because there are limits associated with it. We have to reach certain strains to meet code requirements and in order for the beam to be safe. I know we're running out of time, so I'll mention a few quick things real quick, and then we'll pick this up next time. Beta sub 1, the concept that we mentioned earlier, we didn't use beta sub 1 in that example. We really didn't need it. But beta sub 1, which is the relationship between how deep this is versus how deep that is a function of the type of concrete you have. If you got 4 KSI concrete or anything less than that, beta sub 1 is 0.85. Anything greater than 8,000, it's 0.65. Everything in between, it's just a linear fit. So based on your grade of or your class of concrete, you can determine what's beta sub 1. So if you had 5 KSI concrete, this would be 0.85, but that would be 0.8. Okay? Does that make sense? What? Oh, okay. I think I'm gonna stop for now. But what I'll mention is that there are strain limits associated with steel. There are reinforcement limits associated with steel. You know, we have to provide at least a baseline minimum amount of reinforcement in the beam altogether. Like I said, there are strain limits and what have you. We will use these strain limits ultimately to ensure that A, the assumptions that we're making during our calculations are valid, and B, to ultimately we can rearrange those a little bit and maybe use them for design. That's all I got for you today. I will look at this homework problem and do some digging and see if I'm getting the same answers. And I'll send an email out maybe either with a hint or maybe I can clear some things up. That is all I've got. Everybody, you all have a great weekend. Sign-in sheet is around somewhere, so please turn that back in, and you all have a great weekend again.